Joining today's webinar event. The abstract and the topic that I've got prepared anyway is for reliability testing. And Addison, I think I pronounced your name correctly, but thanks for the idea. I think a nice extension to this kind of high-level topic today will be in the details of how to sort out an acceleration factor given a particular stress or so on. So we certainly can talk about that. And just as a quick startup here, I did a voice check earlier, and Colleen let me know that I was coming through on the phone. Can you hear me all right on the voice over IP? Is that side working? See, a couple people are typing, so. All right, great. Thank you, Yvette and all. Great. All right, before I leave this screen, and I'll come back to a similar screen when we finish, on the right-hand side, you'll see a downloads area that has unique tests slides, and that's a PDF of today's slide set. So you should be able to click that and then download those if you so care to, and a few other contact pieces and so on that'll let you get to or stay in touch and so on. I know many of you are already members of the monthly webinar series email list that goes out, and hopefully you're finding some good content, good topics out there that become useful for you in your career. All right, so I'm going to move right into the presentation, and I'll bring up the download link a little bit later, so no worries if you didn't get a chance to grab the slides. And I'm also going to be posting the slides and a recording up on the Accendo reliability site shortly, probably within a day, once I get the download and get it converted and up to Vimeo and all the other steps. But anyway, welcome. Thanks for joining me today in a discussion about a topic that many of us already face. We do this day in and day out. Many of our roles as reliability engineers is setting up and designing tests and conducting tests and analyzing the data. Excuse me. I think my voice has a shifting problem going from being quiet for the last 30 minutes to starting to talk. But the topic is something that we deal with all the time. We have to work with our management team, with our engineers, with suppliers. We talk about doing reliability tests quite often. So I'm going to dive into that a little bit more and see some of the nuances of that, take a look at some of the issues that come around when we set up and run different kinds of tests. But before that, I want to mention, and I know I've been showing this slide for the last few months, but the Accendo reliability is right now it's an offshoot of my business site, and it's got a series of the webinar recordings and ebooks and a variety of other things, and I realize many of you are already members of that site. I know Kirk knows because I've talked to him about this previously, but there's a few of us that have been working on a brand new site. I'm going to call it accendoreliability.com, and it's strictly for professional development for reliability engineers. So we're going to move the webinar series over to that site and the hosting of them there. Also getting ready to launch a podcast, a series of podcasts basically, so that you'll be able to download and listen to these webinar recordings through a podcast, through iTunes or Stitcher once we get that wired up. Plus, we're working on a new podcast called Speaking of Reliability, where it's a set of conversations among friends. Think of it as we sit down together with you at a coffee shop and talk about the questions you have and issues you have, and based on our experience, and here's our advice or ideas of how to move forward. And I believe I'm up to 18 episodes already recorded, and we'll be looking for more topics and input into that. But keep an eye out for the announcements for that. I expect it to be within the week or so, because just working out the details on the new website and getting everything wired up. So it's getting really, really close to launch. I'm pretty excited by that. And hopefully there'll be a lot more information coming out on that in the next couple of weeks. All right. So reliability. One of the questions, and if you've listened to my previous previous webinars, you've probably heard me talk about a question I ask graduate students in the course I teach is, well, what is reliability? And how is it used in advertisement? How is it used in common language? Now, in our work world, when somebody says, well, how reliable is this system? Or how reliable is that part? Or how reliable is that vendor? We're probably asking completely different questions. Now, from an engineering point of view, what we commonly think about is, well, what's the probability that this will survive a certain duration for some specific function and some environment? We use those 4 elements to specify what we mean by reliability. Now, the people we work with and the people that we provide reliability engineering service to may not fully understand that definition. They basically are saying, hey, does it work? Will it last long enough? Or is it durable enough? Is it robust enough? Is it strong enough? And they'll have all kinds of different nuances to what they mean when they say reliability. So the notion at the start of what we're talking about is when somebody says, hey, can you test this for me? Well, what exactly is it they're looking for? And so our objective is what do you mean? Do you want me to run some reliability testing? What's it for? What are we trying to accomplish? Why are we running this test? Why are we spending all this money? To what end? What is the purpose? And in some cases, early in my career, my boss walked in my office and handed me a sample of a product we were working on, a new development project for a new product, new application. And he said, can you find out if this will last 20 years? I don't know. No, I had no idea. And my first thought was, well, what's my budget? Well, not a lot. Well, how many samples can I make? Well, depends on what testing you're doing. I said, well, when do you need an answer? And he goes, oh, 6 months. And what I didn't ask then, and I hope you ask today if you have this kind of a conversation, is why do you need this answer? Now, back then, eventually it became clear to me is that a major customer was going to buy this product if there was evidence that it would last 20 years in the application. And I didn't really know that. I knew that we wanted it to last a long time. I didn't know how long. I didn't know under what use conditions. All kinds of different things I should have asked as we were setting up and running this test. So I spent weeks developing a way to do testing, and it turned out the test took about 6 months to do. So I was really close to having a reasonable answer, yet it was a little bit too late. And they made a decision to go with the product. The customer was happy with the progress we'd made. I don't think they quite understood the testing we were doing, but it kind of worked out. Now, ideally, the testing that we do is associated with somebody's question that they need an answer to. Basically, is it reliable? Will it last long enough? What's its probability of successfully operating over some period of time under some set of conditions? Now, if I know what those questions are that are needed either by the management team or by engineering or for a purchase decision, then we can create a specific reliability test to answer that question. Now, without those bits of information, well, why are we doing the test? And if there's no real good answer there, well, don't do the test. That's another way to do a unique reliability test is don't do the ones that are not useful. Now, in general, what we're interested in is what will fail. right? What would break down? What's going to fail first? What's going to limit the usefulness of whatever product we're dealing with? And we commonly go into all kinds of different styles of testing, halt testing or discovery, using some kind of discovery process to find out what would fail is very useful information. If you're building the first prototype and the design team comes to you and says, "Here, go figure out its reliability," um, they might be asking about what's not going to work. Where's the weakness? Well, that indicates understanding what they're trying to find out indicates a certain style of testing, right? So I might, if I didn't know that, I might go take this product and go figure out how it's going to be used by a customer and see if it'll last for 20 years. And that may take months to accomplish, and it may not be useful at all for what the engineering team was looking for. So are they looking for what will fail, or are they looking for when will it fail? And those are two fundamental questions that we face, but they're very, very different. And sometimes they're combined. We need to know what will fail in order to know when it will occur. And so if we don't expect corrosion to occur, then testing it for corrosion, accelerated testing, doesn't help us a whole lot to answer the question of when it will fail. And we'll talk more about failure mechanisms a little bit more. So are there other questions? What kind of questions do you get in your working day about reliability? What kind of questions or comments prompt doing reliability tests? And you can use the chat window there. And I don't know if I've ever mentioned this before, but in this platform, you can expand the different windows. If you move your cursor up near the top of any of the different windows, you can expand it, or I don't know if you can move it around, but you certainly can expand it and move things around. So if you're having trouble seeing some of the windows, you can expand them. But use the chat window. What kind of questions do you get that prompt's going to do testing? Yeah. Andrew, yeah, how long will it take? When can I get the answers? Yeah, can I do it with one sample? Those are some of the hurdles that we get, right? About just doing testing at all. How much will it cost? Obviously. Yeah. All right. So one of the questions that we get, and I've run into this a number of times, is that somebody in, say, a program manager or a director of engineering says, we're creating a new product or we're installing a new system, we need to do reliability testing. It's like it's required somewhere. It's written down that that's just part of the plan. And a lot of people believe it's a good thing to do. It's a common thing that we do, so we should do reliability testing. Well, yeah, really? If we can't answer the question as to why we're doing the testing, then you probably don't really need to do the testing, right? If nobody needs the information as to how long something will last or what will fail, well, then there's not a whole lot of point to doing it. Yet we get questions about, after we've decided to test, like how long will it take or how many samples do I need? That assumes that we've already made the decision that we have to do this testing, and then we want to optimize it in some way. But back it up a little bit. Ask, well, why do the number of samples will really depend on why you need the testing. What question are you trying to answer? Do you get those kinds of questions, or is that part of the discussion? Do we even need to do this? And if so, what are we trying to accomplish? Those are two big points here. Right. Now, Andrew and Anand, the types of questions you're asking about sample size or cost and so on makes me think that it's more of that common practice of, well, we just always do reliability testing, or we test, it's just part of the program. This is what we do. But another style that is common is we test it to specification. We run it to the max temperature, we run it to the minimum temperature, we run it so many cycles. If it's a mechanical device, how many cycles is it expected to operate, and so on. We just see if it works over the range that we expect it to work. And some of us would call that environmental testing or test to spec or quality testing, all those kinds of things. And sometimes it's reliability. If it's a connector, for example, that claims it can mate and unmate 20 times, well, we can go into the lab and connect the connector and disconnect it 20 times and then check, does it still work? And that's a reliability test. It doesn't tell us a whole lot. It doesn't give us a lot of information, but it's a common way that we do testing. And I won't ask if this is your style of reliability testing or not. I hope not if you're joining me for these webinars. So another common method is standards-based. Now, again, I won't ask because I know this is very, very common, is we go to IEC or we go to ANSA or we go to SAE or we go to some other standards body and we look up how do we test this, whatever it is. And let's say we're testing some polymer of some sort. And a very common test is to put it in a high temperature chamber, a high temperature soak. And 85C seems to be a very common temperature setting for all kinds of systems. And 1,000 hours is a common requirement. I know with electronic components, 77 samples is, for some reason, is a common sample size in standards. And the claim is that if you run the test for 1,000 hours with this set of conditions and you have no failures, it passes, right? But so what? What do we know? Yeah. What do I know if it runs for 1,000 hours for 77 samples for 85C? What would you do to answer the question? You know, if I was your customer and I come in and say, all right, I noticed this test that you ran and it's by some blah, blah, blah standard. That's great. But what does that mean? How do I use that information to understand the reliability? Yeah, Kirk, you're exactly right. Is that we know it runs at 1,000 hours at 85C, which is probably above my use conditions. Really, anything else? Right? One way to do this, let's say we understand that there's an acceleration factor involved. We know that the failure mechanism for this particular polymer is chain scissioning, which is a chemical process. Oxygen breaks down the chains, and at higher temperatures, that chemical process occurs 10 times faster at 85C than, say, at 25C. And it has some acceleration factor, and there's maybe some model behind that. But I have 77 samples that ran for 1,000 hours. And at the end of the test, my tensile strength or some property that I'm measuring is still good. So I claim it's a pass. But if I know the acceleration factor, I can use the binomial distribution. This is a derivation using zero failures, that the natural log of 1 minus the confidence, the type 1 error, divided by the number of lifetimes times the natural log of reliability. And I can solve this for reliability, and you can too. It's a bit of algebra. So if I do that, I run up the answers to that. If I use 60% confidence that my sample represents the population, so my 77 samples have a 60% chance of representing the population, that the result would be that if it passes, that I have at least 95% will survive some duration of time. Now I've got a 10x acceleration factor, so I'm 10 times the 1,000 hours. So it's 10,000 hours is my lifetime is running this test. And so I'm 95% reliable at 10,000 hours at 25C because I'm using the acceleration factor. Well, that's great. Realize, though, that 10,000 hours isn't much more than 1 year, right? Now, I've run into some suppliers and some folks that will say, oh, no, you're doing that math wrong. You take 77 times the 1,000 hours, so it's the same as 77,000 hours, and then you apply the acceleration factor. And at that point, I start to ask more serious questions. Well, what's the failure mechanism? How does it behave? What's the underlying phenomena here? Is this truly a random failure? And so I go talk to a chemist about chain scissioning, which is the phenomena that occurs with this particular product. And he goes, no, it's a damage mechanism that will change the tensile strength, what is what we're interested in. And it accumulates damage over time until enough of the chains break that it changes the material property we're interested in. So it's a wear-out mechanism. So it's no way a exponential distribution, which allows me to multiply samples times hours and under the assumption that it's a constant failure rate. So be very careful when you see a no failures type test at some accelerated set of conditions as to how it's interpreted. Ask some basic questions of what's the failure mechanism, and then how do we interpret this to use in our situation. Without a little bit of extra work, we really don't know a whole lot. Now, let me ask this question. What's a common sample size that you see in the reliability testing that you work with? How many samples do you typically get to work with? Now, I know if you're from the oil and gas industry, it might only be one or none, which is kind of a moot point. See a handful of folks typing there. Remember to hit enter or pass. Yeah, unless marketing takes them. Good point. Yeah, 1, 2, or 3 is tough. Greater than 30 if you're, for good equals a large sample. I had one test design I was asked to do was on zip ties, these little plastic strips basically that have an attach mechanism on it. So you can bundle cables, for example, with it. And they wanted to compare a couple of vendors. And I ended up with thousands of samples. It was great. But we almost never get that many. And sometimes we'll get 2 or 3 samples and said, don't break it as we go. But let's say, and I worked out the math with the same example. If I have a 10x acceleration factor, I run it for 1,000 hours at 85C, and I get no failures, what does 7 samples mean to me? Well, it means that my product is at least 56% reliable. It's my lower confidence bound, basically, with 60% confidence that I'm at 7 samples without failures under these conditions means at 10,000 hours, I've just shown that it's at least 56% reliable. It could be better, we just don't know. Now, is that enough information to actually make a decision? If I'm looking at a 20-year product, no way. We don't know how it's going to behave out to 20 years. It's just unknown. Even if our decision's at 1 year, would we go to market with a product that would be maybe as bad as 60% reliable? In some cases, yes, that may be adequate, but at least answer that question before you go to run the test. Is this going to be enough information to know? Are we there yet or not? So another one that's one of my favorites is, oh, we always do this. And I've run into this a few times, and I'm sure you've seen it with vendors or within your own organization, is here's 10 things we always do. We test it at 85C, at 85RH. We do a freeze at -40 for 168 hours. We bend it this way and that way 100 times. we give it to a couple of customers and see if they can start it and get it installed. We do on and on and on. Or we use this laundry list of standard tests. These are, if it passes these IEC tests, it must be good. And one of my favorites was the little barcode readers that baggage handlers use. And when that product came about, the team went around and looked for, well, how do I test this thing? We know it's got a risk for drop. So they went and found a standard test for drop testing of portable devices. And it said drop it 10 times onto concrete from 4 feet. And so they went off to the lab, they found some concrete, and they dropped it 10 times, and it failed. It broke apart. So the design team went away and they fixed it, they made it more robust, and it passed that test. And they made some more products and they tested it again and it passed. And over the first couple of years, that was the only test they did until they started seeing that the number one failure in the field was dropping. And so obviously the customers were dropping it more than 10 times. And there was a long, heated debate in that organization about, well, if we change the testing regime, what are we learning? What are we trying to accomplish? If we make the test more difficult, we'll have to change the design. And we can't do that because then we can't compare our design from what we have been doing for the last 2 years to what we're changing in the product. Now, the argument was that was won the day was, well, look, for the last year, we've never failed this test. And customers are breaking the product through dropping. So let's think this through. Maybe the standard test isn't quite useful enough to represent what customers are doing. We probably need to change it. And it took them months to sort out and agree that, yes, I guess we better change the test. And so now, make a long story short, is they test this product, I think it was 15 feet high drop test, and they had to modify the chamber or the room they were in to get more height. They hike it up to 15 feet and release it, and they drop it onto concrete. And it will go 40 to 50 drops without failure. And when they notice a difference, if a new design gives them fewer drops to failure, then it's something's changed, something's not right. If it goes 100 times without failure, then they know they've made an improvement. But without testing to failure and testing it severe enough to actually manifest failures, they weren't really learning anything. Now, if you're still doing just the suite of tests that you've always done, it's time to step back and ask, are you really learning anything, right? Yeah. Now that, they have a benchmark limit. What they've done, Kirk, is they've steadily increased the height and number of drops. They tested to failure, and then they started increasing the height so they would get to failures at some point. And what they found is a very strong correlation to the number of failures at various heights to the number of failures they were getting in the field after a few months. So they're just making their product more and more robust to give the design team feedback on what's working and what's not working related to the accumulated damage they were seeing in the field. Yeah, exactly. It's stress test or step stress. But the basic idea here is if you're looking at your product testing and you're looking at your evaluations that you call reliability testing, one, are you getting results that you really need that are connected to decisions that you and your team really need to make? Right? So if each test doesn't answer that criteria as, well, who needs this information and is the information useful for them to make a decision, then I go back again to, well, why are you doing that test? All right, so let's take a look at a couple of ways to look at how do you create a unique reliability test. Well, one of them is, well, what does the product do? And how do you know it fails? Right? What's the failure mode is a common term we use for just it doesn't function. This lever doesn't create the behavior that we're looking for. Well, how do I measure that? Some of our products are really, really complex. How do I know it's not working, right? And so if that can be a challenge in and of itself. So let's say we figure out, we know that this is a critical function, this little green light has to come on, and when it doesn't come on, we know it's failed. And so, well, what's the failure mechanism? Is it wire fatigue to the connector that goes to that little green light? Let's use a trivial example. If it's metal fatigue, right, is it accumulated damage or shear damage? What's the nature of the failure mechanism? So if it's a button, right, is it a dome switch and does it crack and propagate that crack such that eventually I lose connection? What fundamentally, either the chemistry or the physics of what's going on, is the failure mechanism? Right? Now we need to know that in order to understand, well, what stresses should I be applying in order to cause that phenomena to occur? So if it's a button, right, that's great. One project I worked on was with a series of these little, very inexpensive dome switches. So if you press like a game controller or your TV remote, if you push that little button, it'll snap. It'll give you a little tactical or haptic. I don't remember the exact word, but it gives you a little bit of sensation that it actually acknowledges that you pressed the button and it made contact, right? So if I'm changing stations, there might be a small delay as to when the station changes on my TV remote, tactile. Thank you, Bennett. And so it gives you a little pop that says, yeah, you pressed it. And so I can sense that. So game controllers, you can sense when it's about to do that and then when it hits, and you can optimize your button pushing, for example, on the fire button, for example, haptic. Yeah. And so the notion is that if that phenomena stops working, then that button has failed. It's lost that function for that little feedback pop, basically. And so the idea is that if I take that sensor or that button that's there, that little dome switch, and I put it in an 85C constant temperature oven, it's very unlikely that that metal dome is actually going to change much, if at all. Now, it may start some corrosion process, maybe some of the polymer will break down around it, and so on. But if the basic piece that I'm working with, let's see if I can, is just a dome switch, has a dome phenomenon, and there's a little contactor that if I press this button, it makes contact, and then it snaps back. Now, if that fails, one of the ways that fails, if I look down on this thing, is that this will crack. Should probably change the color of that, make that a little bit, right? If it cracks, if this dome cracks, it may lose its ability to snap or to connect. It may flatten right out and just stay connected, or it may miss the button at all, or it may not provide the haptic or tactile feedback. So by putting it at 85C, it may take decades before that metal phenomena, the spring in that metal, actually stops working. Now that's a completely different failure mechanism. That's some other phenomena that could lead to failure. But if the phenomena is that if I cycle this, I get a metal fatigue that eventually creates a crack, amplificates through that dome and eventually fails, then that's a completely different failure mechanism. And it kind of makes sense to actually just go push the button, right? Either get a little pneumatic device to push it on and off, or if the angle of attack and the force and so on is important, then do some experiments to sort that out. But it's the test that you create has to be related to, well, what's important, what's the function, what's the environment we're using in this thing? So how hard do people push these buttons and at what kind of angles? And then how often do they push it? Right. So I'm looking for what's going to create the failure mechanism. Is it going to be a polymer breakdown or a corrosion or metal fatigue? Now, this is one component and a very simple example, but it speaks to that if you don't know the failure mechanism, it's very, very tough to design a test. So start there. Start with what's the failure mechanism. So then the next step is connected to the use conditions. So like in that button example, when I was working with this group, they had a game controller type device, and it had all these different buttons on it. And they were testing the buttons to 1 million cycles, every single button on the device. Now, I'm not a gamer, but I did watch a few people doing it and played with it a little bit myself and realized that there were some buttons that get used way more than other ones. You know, the little button that helps you do the Wi-Fi connection to sync or to connect your device to the game console, that gets pushed once in a while, maybe once per game session, if even that, right? Maybe once in its entire life. Whereas the A button or the trigger would be used sometimes hundreds of times a minute or more, depending on how fast you were. And so by 1 million for every one of them. It took them 6 weeks to test all the buttons to 1 million cycles, and they weren't getting any failures. And so it was, well, is that enough or not enough? And they didn't know. They didn't know. They've been making these devices for years. They didn't know how many times somebody would push the A button, for example. So we went and figured it out, right? Let's go find out how often somebody pushes a button. And they were doing beta testing on all these different games and new devices and so on. So we were able to record the session of how many times somebody used a particular device and each button over an hour, and it collected all kinds of information. And then we sorted it out and just counted how many times was the A button used, for example. So it turns out that if a person was a heavy-duty gamer and played so many thousands of hours per year and pushed the A button so many times on average per hour, depending on the kind of game they're playing, it was something like 1.8 million times. Now, the other buttons that weren't used as often would be in the tens of thousands in some cases, and then there was a range across the 23 different buttons that were on this device. Yet, given that information, we found that the 1 million cycles wasn't enough to test it for what we expected the heavy user to do over lifetime. And likewise, that most of the buttons had nowhere near that many cycles. Now, if we assume the technology was the same on all these dome switches that were actually the same technology, we could test just the technology, and we did some experiments if the location on the device made a difference and how it was connected to the system for its flex and things like that. But we were able to then create a distribution after all of this data collection as to how often people pushed various buttons. The high end was closer to 2 million cycles, and the averages was around 800,000 cycles. And low ends were just a few times. Some people hardly played the game at all or used that particular button. But it also then gave us a chance to say, well, we want to design a product that works for 95% of our users. Now we knew what that distribution was. And we could test to failure and characterize the number of cycles to failure. So now we had the classic stress strength kind of calculation capability. We knew how people used it, and we knew what the cycles to failure distribution was. Now that's a whole lot more useful than I ran 1 million cycles, or I ran it at 85C, or a standard test of some sort. But the idea is to be able to tell that story for whatever failure mechanism you have. If you know that the dome switch fails due to a crack in the metal, due to metal fatigue, and it propagates due to motion, the cycling of the button. And I also know how it's used. I've done the due diligence to figure out, well, how often do people use this? Now, at first, it was just a guess. We said, let's just watch somebody do it and just sit there and count how many times they pushed the A button. And we got a rough idea, and we were, I think, at about 1.2 million as the back of an envelope, looking at 2 or 3 people running this game, which wasn't bad, actually. It was a little bit conservative on the average, but it didn't give us the distribution. So we spent a little bit more time and energy to find out exactly how this was used. And then we had something really, really useful. So as we looked at different vendors, as we looked at different designs of these switches, we were able to actually compare it to how people use the device and comparing times to failures or cycles to failures to actually make it useful. But if you don't know it to that level of detail, I go back to, well, why are you doing the test? You know, is it just to feel good that it won 1 million cycles? Well, if you don't know if that's too much or too little, how do you rationally make a conclusion as to whether it's useful or not? So the basic idea is, if you're going to create a reliability test, sure, standards and what we've been doing in the past and understanding some of the thought process that went into why we do what we do is a start. But start asking those questions. Yeah, Kirk, we actually did some of the experiments to figure out what the range of force was. We had some people that were human factors type engineers, humans factors engineers, and there's actually books that list like grip strength and button pushing range of uses and so on. So we used some tabulated data to get started, and then we actually started looking at different ways to mount these buttons into the device. So we started looking at, well, putting some force sensors in there to actually measure the ranges, and it was pretty close to the tables that we had available. So we didn't do real extensive work there. We found that the angle of attack was also critical, or if somebody was using a fingernail, so there was a very point concentration of force versus using the meaty part of a finger. But I digress. It was an interesting project, and it was a lot of fun. We got some really good stuff. Yeah. So the notion here is that if you're going to create a unique reliability test, the basic outline is, well, what's the failure mechanism? You know, what is it you're trying to evaluate and model? What are the stresses that apply to that? And then how do you know? Let's check that. Let's validate that model. Let's do some pilots or protos, and does it meet our model and back again? And then as we evolve the test, it doesn't just go into the repertoire of what we always do, is, well, what's changed? We changed material, we changed the design, we changed the support structure, we changed something. Did we change the failure mechanism? So a dome switch can fail because the structure underneath it gives away too much. It just flexes, and it doesn't actually allow the dome to collapse and make contact. The whole structure just moves away. So it feels like you're pushing it. It's kind of a dead switch, but it pushes into the device and it doesn't make electrical contact. Now that's a completely different failure mechanism. So that's the check again type promise. So very, very basic steps. What's the failure mechanism, right? And then what stresses promote that mechanism? Some cases we have multiple stresses. Corrosion, electromigration is I need a voltage potential, and I need a metal that can move, and like silver, if you really want to see metal migration or corrosion, silver is the best one for it, which is why we don't see it on boards too often, but copper can do it too. And some kind of solution to help the motion get started. So contaminated liquid or ions or something like that. Chlorine ions from your hand is often just enough. So I need three elements there to promote the failure mechanism. But then the hard part oftentimes is then, well, how do I relate this to the use conditions? How do I translate an 85°C oven temperature to a 25°C use condition? What's the acceleration factor? Now, if it's purely a chemical process, then we rely on Arrhenius equation and go talk to your favorite chemist. Go find that number. If it's mechanical fatigue, well, we can run that test sometimes to get the failures under different loads and create a relationship to make that happen. But the idea is that you should be able to tell that story of here's the failure mechanism, here's how we accelerated or promoted that failure mechanism, and here's how it relates to use. And if we're barring that, do we really have a meaningful test? You know, is it connected to what we need to do to drive a conclusion? Right. So sample size, you know, that's always going to come up. Duration is always going to come up, and those are parts. Then back to the analysis side of it is, if I only run 7 samples, are you going to be able to make a decision knowing that after a year of use, it's likely to be, all we're going to know is that it's at least about 60% reliable with 60% confidence. Now, is that adequate to make a decision? If it's not, then you need more samples, right? So it becomes a trade-off as to how many samples or how long I run the test, those are elements of it. It's not where do you start when you're designing a test. Yeah, so how do I design a reliability test, Chris, for a failure mode I haven't anticipated? Well, it's hard to do what we don't know we don't know. I think the idea of doing more discovery or paying attention to the phenomena that I see in early prototyping, doing more of the test for robustness, test for in all kinds of creative ways. So if we're doing risk analysis and FMEA and that kind of work, and we ask our designers, well, how do you think this is going to fail? What's your experience tell us? And then we run it down the lab and break it. That's that what will fail, right? Now we find something that fails, and then we take that apart. That's where the failure analysis skills come into play. We figure out, well, what exactly is that failure mechanism? And is that mechanism something that I can build a reliability test about? But if I don't know the mechanism, I don't have a reliability test. Now, I will say, Chris, there's one exception to this. Now, let's say I've got a product that isn't expected to last very long. Say a tank, a military vehicle, or a very, very complex system and device. And if I can just run it in its normal operating environment with normal operating conditions, and if it lasts for a month, we learn a lot of information that's good. Well, let's just run it. We've got a month, let's just run it. And anything that fails now unpeels that mechanism of what are the failure mechanisms I'm looking for. So it's that way to help us find, well, what don't we know? In other cases, we use HALT testing, we use step stress testing, and we have to create a little bit of creativity there to figure out, well, what kind of stresses make sense to use in the step stress. And let's uncover or reveal the weaknesses in the design. But if you're going to answer the question as, well, how long will it last? Will it be 98% reliable at 1 year with 95% confidence? Well, I need to know the failure mechanism, and I suggest you do too. So, you know, do you do unique tests in that regard? As you look at your suite of testing that you're charged to do, are you doing unique tests? Are you answering that question for a specific failure mechanism? How does it relate to the use conditions? You probably are, right? May not be used to articulating it that way, but it's a good practice for us to connect these very, very expensive samples that we're destroying in reliability testing to what exactly is the story about how they relate to the decisions that we need to make in the development process. Right? There are plenty of challenges, sample size, If you only get 1, 2, or 3 samples, as Mark mentioned earlier, well, you got to be pretty darn creative. And if you're lucky, you can measure some degradation of performance. So I can do repeated measures of the same unit and monitor its trajectory to failure. Now, sometimes I don't have that luxury, and the failure mechanism doesn't lend itself to an ongoing reading or sampling like that. Well, then be honest. There's very little I can do to give you a convincing or a useful answer from a reliability test. Now, sometimes when we have very few samples, it's usually due to it's an expensive or complex product. Well, can I take just a sample or a coupon? Can I do it just on the material, the bulk material? Can I create test samples? Can I use subsystems? So in any complex system, we often looked at power supplies, connectors, and fans as the weak links. Well, can I test just the fans? Maybe I can get enough samples to really get a meaningful answer there. And sometimes you're just locked out. We just can't get an answer. But running a set of fixed, don't quite break it kind of tests, I would argue that that's not really a reliability test. So there are sometimes, if you know the failure mechanisms, that you can do repeated measures in a degradation style test. So you can get really good information even from one sample. Other times we just don't have that luxury or benefit. And sometimes we don't have a testing method. We don't have a way to do the testing. And there was a few years ago, I got to work with a group that was making one of these fitness trackers, an armband type device, that was one of the issues they suspected was a problem was that as people put the device on their wrist or took it off, it flexes. It was designed to flex like a soft bracelet kind of thing. But there's a bunch of electronics inside of it, and flexing intuitively is not a good thing for electronics. And so they were concerned about that. So they created a little robot, basically, a little device that flexed the band to its full extension and then back. And I'm waving my hands in front of the screen, which I'm sure you can see, but just think of it as taking a bracelet that's not attached as a ring. It's got, well, I think I can stop waving my hands in front of me and actually just draw it. So let's say it's a very simple bracelet like this, but it's not attached there. So that as it flexes, it takes that end of it and stretches it out. And they made a device that grabbed the end of it and rotated it in and out, in and out, in and out. And they were going thousands and thousands and thousands of cycles, and nothing happened. It behaved just fine. And so they went, I think, 10,000 cycles. He says, well, that's way more than anybody is going to use. Even if you did it 10 times a day, it'll last long enough. And the bands that they were wearing themselves were failing due to flex damage in the electronics. The connectors and the wires were breaking. And it was obvious that it was due to flex, which was inconsistent with what they were doing in the testing. So what they did is they said, well, let's just accelerate how people actually use the device. So they got a bunch of folks and they gave them a bunch of bands and they said, just take them on, put them on your wrist and take them off, put them on, take them off, put them on, take them off. Now what they were accelerating was just the cycles of actual use. And they failed in like 1 to 2,000 cycles. And so the failure mechanism was contingent on that angle of attack, the more complex rotation that occurred, rather than a robot just cycling it through a fixed routine. So it was that answering that question about how do I relate this to use conditions, and then design my test method to replicate how it's being used. In that case, allowed us to do a very quick test that only took 8 to 10 hours to do the number of cycles we needed in order to manifest failures. But doing it the way an engineer thought it would do is let's just extend it straight out and straight in and make a robot do it. Completely missed the failure mechanism. So it's by missing that step of how do I relate this to use conditions, we created a test that really wasn't useful at all, and then backtracked and created one that was very revealing and useful for the team. And sometimes it's the measurement methods. We just don't have it. The challenge can be, well, how do we actually make the measurements? And sometimes it's just a destructive test to make the measurement. Tensile strength measurements is an example of that with polymers. So it's, one, we don't get enough samples. Two, the way we do the testing is either not invented yet, or we're not sure that it actually goes after the failure mechanism we're interested in, or we're not even able to measure it directly. Like this metal fatigue that was occurring in bending, we didn't have a way to sense that as it was in the product. We could use X-ray, but we couldn't see the fatigue damage in the cracks. We couldn't see cracks in the metal. Now, if we took it apart and examined it under a scanning electron microscope, we could see these fatigue lines. But that was a very destructive test method, or a measurement method. So came up with a variety of different ways to make measurements and go after what we're trying to accomplish. But as I'm trying to go after all these different challenges, it's almost always going back to what's the failure mechanism. What do we do to accelerate or measure or promote or analyze the failure mechanism? And if we're not there, if we don't have that basic understanding, we're really just shooting in the dark that this will create a useful result for us. And if we stop at the specification limits and we stop at a fixed number of cycles without running to failure, we're just limiting and more limiting and more limiting the information that we're going to get out of this test. Now, so what's the next steps? What are we going to do about this? Well, for every test, what's your failure mechanism? Or what are the failure mechanisms? And how do you relate it to the use conditions? Now, it might be acceleration factors, it might be angle of attack, it might be a distribution, but connect it to how it's used, right? And then every single test, if nobody's going to look at the results, then don't do the test. Save that money, right? Save that time and energy. Save those samples. Go do something useful with them. But ask that for every test you do. Who's going to use that information, right? And if it does have to be run, is it the information that's needed to answer any questions? So if I want to know 20 years, but it only answers the question out to 6 months, well, is that useful enough to make a decision, right? It does take time to characterize the failure mechanisms. It's to create essentially a physics of failure model for this particular failure mechanism for your application. That does take time. But if you don't get started doing it, you're just not going to have the information you need to create meaningful, useful reliability tests. So, didn't really asked a few questions through and appreciate the feedback, but I'll stay on the line if there's any other questions. And let me pull up the downloads section so you can grab the slides if you want to. It should be on the right-hand side in the download the slides there. It's under unique tests slides. It's about a 7 megabyte file given all the images. And but I have the chat window still open over on the left-hand side. So let me know if there's any questions, and also keep an eye out. Kirk and I are, and a handful of other folks are working on this new Speaking of Reliability podcast. I think I've got 18 episodes recorded. We expect to have it launched if I can ever get this website cleaned up and ready to go. Hopefully, within a few days, we should have it out and available and the podcast launched. So hopefully you get a chance to take a look at that. So you're welcome, Adam. Appreciate that. And the site's not live yet, but it's going to be called accendoreliability.com. And it's going to be a site devoted strictly to reliability engineering, professional development. Webinars, ebooks, podcasts are the first set of elements for it. We also expect to add interactive elements, short tutorials on a variety of topics, a whole pile of other stuff. I've been listening to an Australian podcaster, and he would say a whole heap of good stuff there for you. So hopefully this short webinar made you think a little bit about the testing you're doing and the reliability testing, and a little bit of insight as to what you need to do to create a unique test. And I'm drawing a blank on who it was. Adelson comment that for a future event is to do acceleration factors. Take a dive into those. How do I take different stresses and then estimate an acceleration factor for that, or apply an acceleration factor from the test to my use conditions? So if there's any other ideas or topics for future webinars, let me know. Add it to the chat window, or add it out to to send me an email. I appreciate hearing from you, what you think, what you'd like to hear from.